This is Dr. Holt. This video is on non-conservative forces and the conservation of energy. On the prior lectures I've talked about only conservative forces like gravitational forces and spring forces. In this one we're going to get into the non-conservative forces. The work done by a non-conservative force, which could be friction, which is the most common, equals a change in the energy of the system. We also know that net work results in a change of the kinetic energy. So let me grab a highlighter here and we'll hit the high points of this. We know that the total work net, the net work, will always result in the change in kinetic energy. But we can substitute back in work net as work being done by non-conservative forces and work done by conservative forces. And we set that equal to the change in kinetic energy. But we also know that the work done by conservative forces is always equal to the negative change in potential energy. So what I've done is I've taken out the work done by conservative and just replaced it by let me show you that. Sorry. Replaced it by the change in the potential energy. So the change in potential energy would be defined as final potential minus initial potential, but again we negate that by this definition here. Alright, so here then I've gone ahead and distributed the negative, so then I could say that the work done by non-conservative forces is equal to final kinetic energy minus initial kinetic energy plus the final potential energy minus the initial potential energy. Go ahead and drop the parentheses and I get this equation here. Now, if I bring the finals together, I can say that the work done by non-conservative is equal to final kinetic energy plus potential, let me repeat that. The final kinetic energy plus the final potential energy minus the initial kinetic energy plus the initial potential energy. What that happens is if I rearrange everything, I get this equation here. And this is where we're going to pretty much use in this video is the initial kinetic energy plus the initial potential energy plus the work done by non-conservative forces must equal to the final kinetic energy plus the final potential energy. Now we remember that non-conservative forces transfer energy from the object in motion, just like conservative forces, but they do not transfer this energy back to the potential energy of the system. Instead, non-conservative forces transfer the energy from the system in an energy form which cannot be used to transfer back to motion, meaning primarily that if you have friction, then heat, then this energy is going to be transferred back into heat. And again, friction is going to be the most common non-conservative force that we see. Alright, I'm going to work two problems here, and this should clarify everything. The first example is I'm going to have a 0.5 kilogram bead. It's going to slide on a curved wire starting from rest at point A. It's going to slide down to B. This part's going to be frictionless, and then the segment's going to go from B to C, but this segment will be rough, so we'll have some type of friction involved here. Okay, we know the point A is 5 meters above B and C is 2 meters. So first thing we want to do is find the speed of bead A. Now, to find the speed of BA, we're basically going to do what we've done before. We'll say the initial kinetic energy plus the initial potential energy must equal to the final kinetic energy plus the final potential energy. Alright, this object is at rest. Then this would go to 0, so we can say the kinetic energy is 0 because we have no velocity. The potential energy in respect to B would just be the mass, 0.5, times gravity, 9.8, times the height, which is 5. And we will set that equal to the kinetic energy and the potential energy. Now down at the bottom, the potential energy over here would be 0, and we would have nothing but the kinetic energy at B. So go ahead and do the multiplication over here. This gets us 24.5 joules. That's how much energy we had in the beginning in respect to B. We just set that equal to 1/2 times the mass times V squared. We solve for V. V would equal to, I believe it's 9.90 meters per second. Okay, so that would be the velocity at B. Alright, so now if the bead comes to rest at C, find the change in mechanical energy due to friction. So if we're going to do that, we're going to go back to, basically we're going to use this equation here, and we're going to establish everything at B. Well, we know if we have 24.5 joules here, and we've used this equation to find the kinetic energy, then at B we would also have 24.5 joules. So I can say 24.5 joules plus the work done by non-conservative forces must equal to KEC plus PEC. But again, the object has stopped at C, so can we not say that 24.5 joules plus the work done by non-conservative forces must equal to 0 plus the potential energy, which is going to be the mass, which is 0.5 times 9.8 times the height, which is 2. I'll run that number real quick. So 0.5 times 9.8 times 2, that gives me 9.8 joules. So over here at 24.5 plus the work done by non-conservative forces. Now remember, the friction is doing negative work. Because friction is pointing down, and what direction of motion is going to be up. So since they're in opposite directions to each other, obviously the work is going to be done by non-conservative forces will be negative. So we set that equal to, so then the work done by non-conservative forces, which is equal to minus 14.7 joules. And that's it. That's a pretty straightforward problem. Okay, let's look at one more. Here you have a spring constant of the spring of 15 newtons per centimeter. Now note this is in centimeters, so be careful there. It's going to be compressed 6 centimeters. This mass is 0.5. You're going to release it, and it's going to slide across. It's going to hit this frictional section here, which is which is going to make it slow down, and then it's going to hit this spring compressed. Now this spring also has a different K value of 3 newtons per centimeter. Alright, recommendation would be get this back into newtons per meter. What you don't want to do is say, well, this is centimeters, I don't need to do that because they're going to cancel out. Well, they don't if you think about it, because the spring potential energy is always going to be 1/2 times K times x squared. So you got to convert everything back to meters in this case, because you're squaring the centimeters and they're not going to cancel out. Okay, so I'm going to do this in more of a complex manner because I want to note a couple things. You could go from here all the way over to here. I'm going to do it differently because I want people to note a couple things that you could find out along the way. I'm going to set it up into 1, position 2, position 3 when it leaves, and position 4. Again, I'm going to a lot of work, but I think it's going to be useful because it's going to allow you to find velocities here and here if the question should ask that. So I just go back, we set it up here, we can say the kinetic energy at 1. Now we have no gravitational potential because we're sliding along a horizontal surface, so all we're going to have is going to be the potential energy of the spring. But 1, oops, let me get rid of that, go that right into equal. Go back, change the size of my eraser here. Oh, it does that sometimes. Rewrite that. Plus the potential energy of the spring at 1 must equal to the kinetic energy at 2 plus the potential energy of the spring 2. Alright, so we're going to go from here to here. So the kinetic energy to start out with is going to be 0. The spring potential, we go back to 1/2. We convert our K into newtons per meter, which would give me 1500 newtons per meter. I'm going to change the 6 centimeters to meters, which is 0.06. I'm going to square that and set that equal to the kinetic energy I have here. Now you know at position 2 you've lost all your spring potential, so this becomes 0. So we run that value. That gives me a value of 2.7 joules. I'll run that number one more time to just check it. 0.5 times 1500 times 0.06 squared. Now yes, 2.7 joules. So if I have 2.7 joules here, I have no friction along here. I would, at this position 2, I would also have 2.7 joules. So my kinetic energy at 2 would also equal to that. Now, I could find my velocity if I wanted to. The question should ask it. It doesn't here. But could I not just go back to 1/2 mv squared? We'll put that in as 0.5 times v squared. Set that equal to 2.7 and solve. We take 2.7 times 2, divide 0.5, take the square root of that, and that gives us a value of, let me do it one more time, 2.7 times 2, divide 0.5, take the square root. That gives a value of velocity of about 3.286. I'll say 3.29 meters per second. Now the question should ask, if a question should come along to ask you that, that's how you would find the velocity as you leave the spring. Okay. Now we're going to go from 2 to 3. Again, we have 2.7 joules of energy here. We go back to this equation here, and we can just say that 2.7 joules that I have at 2 plus the work done by the non-conservative forces will equal to the at 3 I'm not going to have any spring potential, so just be equal to the kinetic energy I have at 3. So now down below I've kind of drawn up, clarified this, enlarged it a little bit. Now friction is going to be doing negative work as it slides along here, so let's find out what the frictional force is going to be. We know that friction is going to equal to the normal force times mu. Now the normal force is just going to be 0.5 times 9.8. That's our normal force. Now our coefficient of friction is 0.18, so we'll go ahead and do that. And that is going to give us a value of 0.882 newtons. Now that 0.882 newton is going this way, but your object's moving this way, so the friction is doing negative work. And how far you're sliding? You're sliding 3. So the work done by the non-conservative force is going to be nothing more than negative 0.882 times 3. Again, I'm negating that because it's going the other way. So that gives us 2.6, or negative 2.646 joules of work. So we'll come back here, 2.7, and I'll add the negative, minus the work done by the non-conservative, is equal to the kinetic energy I have at 3. So 2.7 minus 2.646 only leaves me 0.054 joules of work, not work, energy. So if I want to find the velocity, again, all I'd have to do is go back and say 1/2 times the mass, which is 0.5, times velocity at 3 squared must equal to 0.054 joules. We'll run that for the heck of it, times 2, divide 0.5, second square root, second answer. That's going to give me a value of about 0.465. So my velocity at 3, if the question should ask it, would be 0.465 meters per second. Alright, but again, the main question was to find the spring, how much it's going to compress. And again, I'm going through a lot more steps than I would expect a person to do if the question should just ask you for the compression, because you could just go from 1 over to 4 and include the work done along the way. Alright, but now let's go back to, and we're going to go between 3 and 4. To go between 3 and 4, let me erase this, I'd done this earlier. To go between 3 and 4, can I not go back and say, well, at 3 I got 0.054 joules worth at work. So I can set that equal to what's taking place here. Well, the box, as it hits here, is going to come to a stop, so the kinetic energy here would be 0, and all we would have would be spring potential, so that'd be 1/2. Now the K value of the second spring is different. It's going to be 3 newtons, so that would be 300 newtons per meter times my deflection squared. If you run those values here, let's do it real quick. So that's going to give me 0.054 is equal to 150 times x squared. I take 0.054, I divide 150, I take the square root of that. That's going to give me 0.01897. We multiply that by 100 to get centimeters, and that's going to give me a value of about 1.90 centimeters. And that it would be the deflection of the second spring. Alright, that concludes this video. Again, I worked a couple problems. I've defined how to set these up using the non-conservative work. Again, if you consistently set it up using this, it's pretty hard to make a mistake. Just remember though, the non-conservative forces, when you have friction, is going to do negative work. Alright, well, best of luck with this.